Okay, you got it?
Yep.
Hi, Abby. We're reviewing for Wednesday's physics test. And the first, number one, you'll have to get this handout from someone or from Miss Tammy before Wednesday. I'll leave one for you there. Number one is a sea captain's wheel. So when you are a sea captain and you're holding onto the wheel, you've got one hand at one spot, and then 180 degrees later is another spot, or your hand. So you can't have your hand on more than two spots. So you are going to be applying force as pictured on the little diagram there. 92 newtons of of force, and applied 42 centimeters from the center of rotation of that wheel. So you're asked to find the total torque. So in order to do that, you have to remember that torque. Is that showing up at all?
Not really.
No, that's a bummer. Okay, well, she can just gather from what we're saying. And I can try to darken it while you're working. This is a formula for torque. The wavy hat T is the symbol for torque. Equals force perpendicular times radius. Is that any better?
Yeah, that's showing up a little bit now.
All right, Abby, I'll try to make it visible as much as I have time. So we're trying to find torque on that. Notice there are two torques that you have to calculate, and you have to add them together. So you have to take the force perpendicular times the radius. Let's make sure that we work in meters so that we can have the proper unit in the end. So go ahead and switch the centimeters to meters and apply the formula. You do that at both spots. Also, you must remember, is this creating a positive torque or a negative torque? So I kind of drew my thinking here. Here's my thinking. I changed my 42 to 0.42. Are you okay with that? 0.42 meters at both spots, and we still have 92 newtons of force at each spot. So that's just a picture, changing centimeters to meters, basically. Alright. Doing the work, what sign are given these torques? If this was the only hand on the wheel, the only force, do you notice it would make it rotate this way? Is that a positive torque or a negative torque? Did we decide? Positive because it's going like the clock. So this one creates a positive torque, so I'll indicate that. And what does this one create?
Negative.
See, look, it's going this way.
It's still going.
Yes. Yeah, so notice, don't let that trick you. Just because they're opposite each other, they're going in the same direction. So we have two positive torques. They're both going clockwise. So what sign are given the torques? Both are clockwise. So now we're ready to actually add the torques together. So the first one is 92 times 0.42, and the other one is 92 times 0.42, and you add those together. So when you do that, see if you get the same answer as I. Questions on how to calculate torque? These formulas are gathered for you in the corner of your handout. So if we come upon any that we haven't. All right, I'm going to darken this for Abby. This is the last line. This is where we actually calculated the torques, Abby. All right, and did you get, as I did, 77? All right, but you're not done. If you give me that answer on the test, you will lose a little bit, at least half a point, because you need a unit. So let's review what unit does come with torques. If you look at the original formula, force times radius, think to yourself what units that is. So Hannah, what is it?
Is it Newton meters?
It is Newton meters. 77 Newton meters. All right.
What equation is that?
It's this one.
There you go, 77 Newton meters. Did you get that before I did? If you were able to get that before I did, you can give yourself a tally. And if you were able to get the unit as well, you get a second tally. I won't do that for everyone, but this one. So, two tallies, start gathering your tallies. Number 2, where is force applied most efficiently? I don't have a handout for this one, Abby, so. Well, where is force applied most efficiently? I can draw it for her. This is not, I'm not drawing on the glass, don't freak out. Alright,
I was
so.
about to freak out.
So in part A, we'll call it, the force is applied, here's the radius, the force is applied like that. In part B, I'm running out of room, I had to make it squishy. The force, here's the radius, but the force is applied like that. So force and force. On which one is the force applied most efficiently? Make your selection, A or B. And I'll tell you the answer and why. Can't move that down. Move the whole machine down. There, A and B, Abby. Alright. The one that uses the force most efficiently is selection A. This one right here. The reason is that the only force that counts is the force that's applied perpendicularly. So there is some element of this force that is applied perpendicularly, but you have to break it into its components. Like one would go this way and one would go that way. And the one that's perpendicular is this one, but it's shorter. It's shorter. The perpendicular component is shorter than it needed to be. So this A is most efficient. So give yourself a tally if you chose that answer.
So B is shorter than too short, is that?
Yeah, the force is much shorter on B than on A. So A is the correct answer. All right, number 3, we have one of the seesaws. We called it a still stick. So let me get my still stick up here. Well, number 3, we have someone with 32 kilograms, 1.32, can you see that? Meters away from the fulcrum. And then we're not sure where to place the 41 kilogram person. What'd she say?
She said that they're probably gonna end up skipping second and then part of third. But she sat there on the phone with Miss Armstrong, talking through 5 of the different scenarios. It took me forever. I'm sorry.
Okay.
Yeah, they hadn't really planned it out until I came to the office next.
Okay. All right, thank you.
Yeah.
So it's sort of, it's not a 2-hour delay, just skip 2 and part
She
of
said
3.
she'll send a definite email today,
Okay.
but that's probably what it's gonna be.
Okay. All right, let's see what we got here.
Can I see?
I love
It's
it. You do?
totally-
Really? Why?
All right, number 3. We're working on number 3. We're getting tallies,
Let's go to IHOP.
Annabella. So,
Okay.
all right. Sum of the torques equals MA is what happens when we have rotational motion instead of sum of the forces. So sum of the torque is MA, and we're trying to figure out where to place the 41 kilogram guy. So we're going to add up the torques in order to do this problem. Torque, again, we had a formula there in the corner that says it's force times distance, or radius. So because it's balanced, the sum of the torques is going to be 0. There's no acceleration. So we're going to first of all remember when we're dealing with force, we need a weight. See, the torque involves a force. Yet I did not give you force, I gave you mass. So first of all, let's change 32 kilograms to weight. So weight equals mg, do that and I'll reveal the answer. You're going to change the 32 kilograms and the 41 kilograms to mass. Is anyone timing this?
Yeah, we're right at our limit.
Okay.
Yeah.
All right, shut it down.